Good afternoon. Thank you very much for coming. This is my first visit to the continent of India, and it's been very exciting. I was in Bangalore, where I saw several of you just last week to celebrate the 60th anniversary of one of your most famous material scientists, Didi Sarma, and it was a great pleasure to see the Indian community and some people from India that I knew from papers, but not in person, so that was very exciting. So what I'm going to tell you about is first, I'll start with some introduction about colloidal nanomaterials, tell you a little bit about why we think it's interesting. And then I'll mention one specific topic that we work on, which is infrared applications of those materials, which nobody else is doing as far as I know. And so it's probably the only time you'll hear about it until someone else picks it up. This is Chicago, by the way, on a typical gray day. And the university is about 10 miles, it's about 10 miles, 8 miles further south. This is seen from the northeast. So this is the outline. I'll tell you a little bit about transport afterwards and mid-hour detection. So the general motivation of all of us who work in this area, which is at the interface of chemistry and physics, is to think of the future in terms of devices. Currently, all devices that are high-tech are made top-down by fancy lithography technique. But we know that there has been some very significant revolution in science due to nanomaterials, but not the nanomaterials that I'm going to tell you about. Nanomaterials which are made by two-dimensional structures, such as the quantum wells, for example, the quantum wells that we use in this little laser pointer. The layered superconductors, not quite a revolution technologically, but certainly scientifically a very important discovery when it was made in 1986. Giant magnetoresistance, which was the start of a great increase in density of hard drive capacity. And then more recently, graphene. Each one of those discoveries led to a Nobel Prize, by the way. And so this is still today the main areas where nano has had a huge impact in technology. Now, what I'm going to tell you about is colloidal nanostructures. And so these are all those little things here that several of you work in the laboratory. And they have pretty colors, and they have interesting shape. And the challenge that we face is to use them in a way that is useful. So it's a very new field in a sense, started around 1980. But it's also a very crowded field. There's already about 200,000 papers on colloidal nanomaterials of one kind or another. Now, if you think of that, a PhD student publishes on average 4 to 5 papers as a PhD student. You divide that number by 4 or 5, and that makes 50,000 PhD students specializing in colloidal nanomaterials, out of which you and I are some of those. So it's a huge amount of people. Now, there is interest in biology. The first paper I saw with titles containing the word nanoparticle was actually a biology paper, thinking of drug delivery. And today still, there are lots of research on trying to use nanoparticle for drug delivery or as drugs by themselves in biology. The colloidal quantum dot topic is the topic that I'm familiar with mostly. And I'll mention that more in detail later. The word itself, quantum dots, was coined in 1986 by Mark Reed. Carbon nanotubes were the ones that actually started the nanotechnology revolution with fantastic promises, in particular by Richard Smalley, which I'll talk about again in a minute. And then metal nanoparticle is the more recent, past 15 years or so, crazy field that is extremely popular with lots and lots of publications. So the field is vibrant. There's lots of work done. It's fairly recent. And it also grows strongly in India. So just in India, I found about 12,000 articles from the Web of Knowledge. So there's a lot of work done here. That's about 5% of the total output of colloidal nanocrystal material. It went very quickly. Before 1998, there was only about 20 papers. One of those was actually by Didi Sarma, one of the first papers that pushed this topic in India. So myself, let me introduce myself. My background was not in colloidal nanomaterial because I did a PhD in 1984, which was before this became really popular. But it was in surface nonlinear optics. But when I went to the University of Chicago, I started working in this field. And at the time, there was really very few groups working in this area. In the US, there were maybe 3 or 4 groups. And I started, and we did a number of original work at the time, trying to look at the single particles by fluorescence, and then so on and so forth. Why is there so much interest in colloidal nanoparticle? Why is it so popular? I think first it's easy to get into it. Right? It's, all of us can make nanoparticles that nobody else has made. We just mix things, and then they aggregate, they precipitate, and they form some sort of structure. And if we have the tool, and that's very important, we need to have the tool. We need to have a transmission electron microscope to see them. Many groups have had difficulty advancing in this field because they didn't have imaging. But I think nowadays that kind of tool is standard in universities that have reasonable instrumentation. So if one has that tool, then it's really easy to get into the field. It's not a very costly topic. It's also very open. There's a lot of serendipitous discoveries that can be made. In fact, nearly all the discoveries on shape control or on Kirkendall effect, the exchange of ions, those were serendipitous. They were not done. It's not like someone tried to observe new shape or tried to observe the exchange of ion in the nanostructures. It just happens. And so with a good eye and a good instrumentation to see the structures, one can make discoveries. And it is also full of fantastic promises made by people who are very respected. So it started long before this era by Richard Feynman, who wrote that book where it says there's plenty of room at the bottom, thinking, well, we know the structures we see and we can handle, but then at very small scale, there's a lot of stuff that we didn't know how to do then, and that maybe now we're much closer to be able to do it, to control matter on a very small scale. And then the other very famous scientist was Richard Smalley, another Richard, who wrote this very confident statement, which basically say that nanotechnology will impact everything in a larger scale than anything that happened before. So this, and then the funding. You don't have a popular field unless it is funded. And because of all these promises, and in particular the big role played by Richard Smalley, the US launched that nanotechnology initiative, which really settled the attention on the topic. And I think many countries followed. So is it more noise than signal? Right? Is nanotechnology just a hype, or is there still some signal? I mean, with this kind of publication level, you could wonder, there's a lot of noise for sure. There's at least 3 real nanoproducts that I know of, which are titanium oxide self-cleaning surfaces and silver and zinc oxide antibacteriological powder. Well, that's not really a big deal. There are niche applications. So for example, quantum dots can be used to highlight features in a cell because they fluoresce, and so one can see them very nicely in a microscope. And there are applications for magnetic imaging, trying to have magnetic nanoparticles, such as iron oxide, embedded into biological tissues, and they will modify slightly the MRI images by their presence. But these are not yet large-scale applications. There are some ideas which are struggling, trying to use quantum dots for light-emitting diodes to have big, cheap, flat panels. But they do compete with OLEDs, and that's a hard competition. And there are fanciful promises, which many of us take advantage of when we write grant proposal. We want to solve the energy problem. We can propose to do this by photovoltaics or by photocatalysis, trying to make water-splitting quantum dots. Or for those of us who are interested in biology, we want to solve cancer. And so there are proposals such as photodynamic therapy, where you inject something inside a body, and somehow you find a way to guide those things to let them target cancer, and then you shine light on them, and they heat up, and they destroy the cancer cell. So those are still promises at this stage, but there's certainly a lot of research on those topics, but not yet actual applications. So noise or signal, it's debatable. Is it a bubble? With that many publications, that much excitement, you wonder. So what is an economic bubble? It's a surge in equity prices, et cetera, followed by a drastic drop in prices as a sell-off. So let's try to see what a scientific bubble is. I'd say it's a surge in a fashionable topic, often more than warranted by the fundamentals. In other words, the science doesn't justify all of the excitement. And usually in a fairly easy sector where a lot of people can move in quickly, followed by a drastic drop in interest as a new discovery occurs. So that's a question. Is colloidal nanomaterial a bubble? To give you an example of the popularity, this is crazy. This is plasmonics. This is a paper that has no fundamentals in the sense that it's a review paper. There's not a single equation. It's a very nice paper. But it was published only 5 years ago and already has 2,500 citations. So it's a paper that contains no fundamentals, but it is extremely popular. So why is that? Because there are a lot of people. I mean, if there are 2,500 citations, that means there's 2,500 papers that think it's a likely outcome. And of course, nobody has made improved photovoltaics with plasmonics yet. Now, I had fun looking at citations and papers doing this, preparing this talk. And this is another very interesting paper, very similar, the photoelectrical effect on ultramicroscopic metallic nanoparticles. Try to guess when that paper was written and who wrote it. Well, you won't guess unless you know, but you certainly know the famous name of Gerlach. In the early 20th century, the Stern and Gerlach experiment discovered the spin. Well, this was written by Gerlach and in 1914, so 100 years ago, but it has only 20 citations. It is in German, so I couldn't read it in detail, so I don't know if it had the concept of plasmonics, but it certainly had the concept of field and photoionization. So is the quantum dot bubble going to, photovoltaic bubble going to burst? Well, possibly. Because there's been a new discovery, which is the perovskites. And so this is currently the number of citation per year if you search quantum dot and photovoltaic. And the number of papers, not citation. The number of citation is about 15,000 now. So this is the number of papers, a huge number of papers written. My guess is that in 2016, we will have reached a peak and it will drop down. And then we'll be left with doing the good science. This is actually a paper by Prashant Kamat, a very famous Indian scientist who works at Notre Dame. We're not far from Chicago, just about an hour and a half away. And that review paper, written only about 6 years ago, has already 1,200 citations. That means it's a very popular field. So nano is useful for marketing, for sure. The question is it useful for something else? So if the nanomaterial does not hurt the performance, it can be used for marketing advantage. So you have the iPad Nano, the Tata Nano, and the Nano Polish, and carbon fiber enhanced with carbon nanotube or graphene nowadays, which makes you buy more expensive tennis rackets or bicycles. And there's even, now when I went to Delhi airport, I was very pleased. I saw this thing, so I took a picture. And it is this new technology advanced by Samsung where they use nanocrystal to apparently enhance the color. I have not seen the real TVs, so I don't know if it makes a difference. Has any of you seen the TVs with quantum dots in it? No? Well, I haven't, so I can't tell whether it really makes a difference. But when you read this, it sounds good, right? Sounds like you're willing to pay an extra $500 for that TV. And so, powered by nanocrystals. And so, I'll move to the topic of quantum dots. That's the topic that I'm going to focus on. Out of all those colloidal nanocrystals that you could imagine making, quantum dots are the ones where you control the size of the particle, and the electrons are wave, and so they sense the boundary of the material, and therefore there's a wave frequency associated with the size of the particle. And so it's really like a drum, or I learned this new instrument, the bansuri, right? It's a wave inside a confined space, and that wave has to have a specific frequency if we solve the Schrödinger equation. So we have the case for an atom, where the confinement is due to the Coulomb potential with the nucleus, and for a particle, we have the confinement due to the sphere. I'm sorry, I apologize for those of you who know this very well. I was told there might be a high school student, so I don't know. Anyway, I won't spend too much time on this. The fact is that it works beautifully, and this is the work by the MIT group from 1993, probably the most significant paper in that field, where they showed this exquisite tuning of this color of the nanoparticles with simply changing the size. And so here they were going from 17 angstrom to 150 angstrom of particles controlled at the sub-nanometer resolution. And you can see the color changes. Now normally, in chemistry, if you want to change the color, you have to change the composition. You make an organic dye molecule, or any kind of dyes is a different molecular compound. Here it's the same chemistry, it's just simply changing the size. And so it makes you dream, of course, that it's a lot simpler than doing this fancy organic synthetic chemistry. And moreover, of course, each of those spectra can be understood because of the physics underlying it. So we can understand much of what the little structures in those spectra come from, and they come from states in what we call the conduction band and the valence band. And later I'll focus a lot actually on the few states here in the conduction band. The synthesis is simple. That's why there's so many people can move into it. It has evolved quite a bit. In 1980, when this started, it was really mixing salts and glasses together, heating it up, and letting the salt initially dissolve into the glass. And then as it was annealed, eventually this salt would aggregate into nanoparticles inside the glass. And this led to color filters. It took Ekimov and Afros in 1980 to realize that those color filters arose from quantum dots. And they also did an extensive study of copper chloride aggregates. And this saw excitonic spectra shifting with particle size. Soon after, the colloidal synthesis in solution really emerged through the work of Lou Bruce, Arnim Hangline, Art Nozick, and several others. And there was another technique, micelle nanoreactors by Marie Pellini and Lou Bruce. And in 1993 is the work that I mentioned, the work by the group at MIT, led by Munjiba Wendy. There, they completely changed the way we look at the synthesis. They used an organometallic approach, which involved toxic, very toxic and pyrophoric reagents. And so they were very brave, and they also were very adventurous in trying different things. But it worked beautifully. It gave the best results. In 1996, we introduced this core shell idea to passivate the surface with a material that had a chance to be epitaxially registered to the lattice, and that led to robust and much enhanced luminescence. And probably the most important development in this area was then the introduction of salt reagents by Xiaogung Peng. That was important because it made it a lot easier for a lot of people to start working in this field. If you had to work with dimethyl cadmium, which is this pyrophoric thing that when you take it out in air, it will spontaneously burst in flame, it's a barrier. But if you can work with a salt of cadmium, then it's a lot easier. And so since 2000, I think the field has exploded, where a lot of people, a lot of groups have moved into it, not only because there's funding, because there are a lot of promises, but also because it's very easy to make nanoparticles of semiconductor. So moving fast forward, where are the challenges in the future? You know, it's very hard to predict the future, especially the future. But solution process luminescent materials are certainly interesting. Right now, cadmium-based compounds are the most popular. They're probably the ones in the Samsung TV, but that cannot last very long. They will have to be made with less toxic materials. So we need luminescent, less toxic material with 100% or close quantum yield to make good phosphors. That's going to be very difficult, and they compete with OLEDs. There is a synthetic challenge to make 3,5 materials of good quality. For example, gallium arsenide. It still does not exist as a nice colloid. There will be challenges to make multi-element compounds, such as, for example, this CZTS, copper, zinc, tin, sulfur, or selenide. This is made out of less toxic materials, widely abundant. And in principle, this material should be tunable through the visible spectrum to lead to luminescent nanoparticle, but nobody's done it yet. Why? Probably because composition, surface, size, distribution of the uniformity of the composition are not controlled yet. There will be applications in the near-infrared for biology, trying to see through skin to some depth without being absorbed by the pigment in the blood. So, for example, silver sulfide selenide might be an option, and they are being popular now. And as a long-term goal, all of us, so far we make nanoparticles by synthesis in liquid, but you know, the dream will be to have a solid, which is where we know everything. where we know the crystal structure of the nano composition, and then it's modulated on a nanoscale so that we can tune the optical properties the same way we do with quantum dots. We could put magnetic impurities to change the magnetic properties. That would also allow to control the thermal properties with applications for thermal, electric, optical, magnetic, etc. So that's kind of a dream goal, but that's far off to control the chemistry at that level.
Can you please explain the point number 4?
Which one? This last point? Or the non-blinking or blinking on demand? Well, non-blinking is a difficult topic. So quantum dots, when you look at them with an optical microscope, they blink. They are bright for a while, and then sometimes they turn off. And this remains to this day a mystery. It was discovered about 15 years ago, still remains a mystery. Now, there's been progress over the last few years to make nanoparticles that blink much less. But they tend to no longer be quantum dots, in the sense that they're so big that the confinement becomes very weak. Now, sometimes it is good to have something that blinks because you know you have a single one. But it's not so good when it blinks in a random fashion. So if you could make it blink on demand, then it would be a great instrument for super resolution microscopy. Because then you could turn them on, turn them off, and see their position with great accuracy. So the first topic I'd like to discuss briefly is conduction in quantum dots and nanocrystal solids. So that was a topic that was quite interesting in the mid-1990s. One of the first observations that was significant was the work of Jim Heath, who realized that you could take silver nanoparticles and put them into a film and compress the film, so increase presumably the interaction between the silver particle, and it went from being insulating to metallic. And you could see this in the reflectivity of the film, which was initially not particularly reflective and suddenly turned very silvery upon compression. So that was very striking, and it raised a lot of questions. But then it led people to believe that quantum dots would also show this kind of metallic conductivity quite easily. But the fact is, for the next 5 or 6 years, quantum dot solids were only extremely insulating. And one could observe some sort of current going through, but only when photoexcited and under very high electric field, which is a situation very similar to the situation that organics faced before the work of the Heeger, McDermott, and Shirakawa. In other words, organics were the same. You could observe conductivity, but you had to apply such a high field to pull the charges through. And you had to photoexcite the system also. And so in 2003, we were asking ourselves and the rest of the community, why is it easy to make a metal nanocrystal solid, metallic, but quantum dots difficult? And so we addressed this issue with doping. The first thing you need to do if you want to have a solid that's conductive, you need to know what its Fermi level is. That's basic solid-state physics. And so we knew that. And the only question was, how do we change the Fermi level? Well, you change the Fermi level by putting charges in or taking charges out. And so that first challenge was how to dope it. And you can dope by charge transfer. And so this was done in 2000. You take a quantum dots, you find something that is sufficiently reducing so that the electron can go into the dot. And for the first time, we were able to see the effect of this occupation of electronic states by the electron into the optical spectrum, with what is here we call the intraband transition, which is a transition between the states of the quantum dot at this level. So here I'm getting quite technical. And that transition is a direct evidence that there is an electron here. So we knew how to dope, but it was not very convenient because that was done in solution. We then went to a solid on an electrode inside an electrochemical cell to try to dope it. And when we do that, we apply a potential. The potential is such that electrons will jump from the electrodes to the particle and maybe from particle to particle, and the film is thick, so it will go many layers of particles. But the problem was this was very slow, which means the electron was hopping very, very slowly. So slowly that it took several tens of seconds for the film to change color, which is what happened when charges are injected inside the particle. And then we realized something very simple. We just changed the distance between the particle with a small ligand, and that was done in a very simple way, simply dipping those films into a solution and then you find that the response time drops by about 3 orders of magnitude. So now, instead of being tens of seconds, it's tens of milliseconds. So that was the first hint that if charge transfer can be that fast so that the film can change color in tens of milliseconds because of charge injected all throughout the film, then it might be conductive. And so indeed, the same kind of films were then measured for conductivity by putting them onto interdigitated electrode and applying a small bias across. And what we saw was this very nice demonstration of conductivity where the, so I have a little animation here. These are the Fermi level of the electrodes. When we apply a bias, we're going to raise them to the point that electrons will start being able to hop onto the nanoparticles all the way through. This is what happens on this part here. And at the same time, we could monitor the spectroscopy and see that those states are indeed being occupied. And then what was particularly nice and expected, but very nice, is that when that level became full, and we could see this by the saturation of this optical bleach, when that level is full, the conductivity dropped. And so you expect that. You have 2 electrons per state. The state can only take 2 electrons. It's filled on the left, filled on the right. No matter how much you push or pull, the electrons can't move. But then, of course, the next state is not infinitely high. And so then if you will see some current from it, but also if you raise the bias a little bit further, then you'll see additional conductivity coming from those states. And so the fact that the conductivity is higher here is in part because these are electrons that have high energy. They can hop more easily, and there's also a higher degeneracy of state at those levels. And then it was easy to change the ligand to try to see how much one could change the conductivity. And this was an example going from an alkane to a conjugated molecule, and you can easily get 2 or 3 orders of magnitude improvement in mobility by adjusting the ligand. And this has been pursued by many other people, and it's not totally standard. Everybody does that. So the first one to follow was the group of Bawendi, who published photoconductivity studies on this, and they made it clear that it's not so much the need to have some molecule that binds the 2 particles, but just making the particles closer together. And then many other improvement, and nowadays probably the most important developments is this use of inorganic ligands instead of this organic ligands. So we have inorganic particles, and right now we kind of make them conduct electricity by having the electron tunnel through organic molecules. Well, it sounds like a mixture of 2 things. Why not going fully inorganic? And this is the work of my colleague Dimitri Talapin at the University of Chicago, who developed his chemistry to make fully inorganic solids using some decomposable chalcogenide ligands or other kinds. And so nowadays, the mobilities, which is a measure of how easy the electrons travel through the materials, are becoming quite high, 30 centimeters squared per volt second. The challenge, I think, with such high mobility is to be sure that the electrons are actually flowing through the quantum dots rather than around the quantum dots. And I think this is still a question that has not been resolved. In our systems, and in all the systems that show fairly low mobility, then the transport is definitely a hopping transport. It is not the solid state physics level of transport where you have band transport. It's hopping, so the electron is in the particle. It's thermalized to its lowest level. It becomes thermally activated to hop onto another particle. It thermalizes again, so there's absolutely 0 coherence between hops. It's really just total classical hopping. And there are different regimes depending on the temperature, from Arrhenius behavior, and as you go to lower temperature, we enter the regime of what is called variable range, where the electron might choose to go further away just to find a state that is within kT, rather than hopping onto the nearest one. But of course, it pays the cost of a longer distance to tunnel. And so then there's also different kinds of variable range, the Efrosh-Shklovsky, where Coulomb interaction dominate, or the Mott regime, where just the density of state dominate. And we showed that if you tune the density of state by picking the Fermi level across the dots, so you have, when you charge with very small number of electrons, you're in the Mott regime. Then when you have of the order of 1 electron per dot, you're in the Shklovsky regime. And then with 2 electrons per dot, you're getting the minimum density of state, and so on and so forth. So Transport in quantum dot solid is now standard, and it can compete with organic materials. It's ubiquitous in research involving photovoltaic, light-emitting diode, electrochromic materials, and field effect transistors for electronic applications. So now I'd like to tell you about the last topic, which is this infrared application of quantum dots, something that I think nobody else is doing yet. Why do we study infrared quantum dots? Because it's cool. It gives you a different view. So this is the picture I like. This is me inside a garbage bag. And you don't see what I do, but I'm holding my hand up with a certain number of fingers. And if I have an infrared camera, I can see how many fingers I'm holding up. I'm holding this. And the reason why the infrared goes through is that this is a polyethylene plastic, so it has absorption in very specific infrared range, and it's black because it contains some carbon black, but carbon black has a uniform absorption across, which is not that much. In infrared, it's less. And so you can see the heat radiated by the body inside the bag, and the radiation, the infrared radiation goes through. That's why it's fun. This is my lab, by the way. The other reason is I've always been interested in infrared since I was a graduate student. And you always work on your PhD thesis, and you work even more on it when you get older. So that's what happened to me. So I work on my PhD thesis again. I'm working on infrared spectroscopy nowadays. And then it's also important. It's important because infrared is used for thermal imaging, for night vision, astronomy. And the reason is, shown here, is that the atmosphere is surprisingly transparent in the infrared. Even though our eyes can't detect it, the atmosphere is quite transparent. You can see straight through to the stars with infrared between 3 and 5 micron, except for the CO2 absorption here, and from about 8 to 12 micron, 14 microns. And so it's a good way to look at through atmosphere. It's a good way to communicate from Earth to satellites. So one day, instead of microwave, we might be using infrared beams. And it's a good way to see warm bodies at sea level. So for example, a temperature of 300 Kelvin, human body has a peak of radiation at 10 micron, but of course it radiates everywhere. And a body of 1,000 Kelvin, of course, would be around 3 micron. So the technology for infrared detection is quite limited. There's really two main technologies. One of them is very expensive, but it's very good. It's very sensitive at the limit of what we call background limited sensitivity, where the noise is really coming from the background radiation. But it's very expensive. The material itself is expensive. And the assembled devices, which require liquid nitrogen cooling or some sort of Joule-Thomson expansion cooling, are also expensive. So $50,000 to $100,000, that's the price of a camera. They're also very fast. Now, there's a very cheap technology which has evolved wonderfully over the last few years, which is bolometers, but they are slow. So if you wave your hand like this, you just see a band that is blurred. They're also not as sensitive, about 10 to 100 times less sensitive than the quantum detectors. And they're much cheaper. So nowadays, something like this would be about $3,000, but you can get even cheaper camera, not video cameras, but cameras that you can apparently add to your cell phone for a few $100s, which have about 100 by 100 pixels. So why quantum dots in the mid-infrared? Well, first, quantum dots are good when there's no other competition, and from solution process material. And so there's no organic competition in the infrared, that's for sure. Organics cannot work in the infrared. Does anybody have an idea of what the highest luminescence quantum yield for an organic dye at 1.5 micron, which is not even entering the mid-infrared is? So 1.5 micron photoluminescence quantum efficiency of a dye, the best number. Oh, it's about 10 minus 5. So it's really inefficient. And the reason is very simple, is that as soon as you have an organic structure, there's a carbon-carbon stretch, 1,500 wave numbers. There's a carbon-hydrogen stretch, 3,000 wave numbers. And 1.5 micron is just 2 vibrations of the carbon-hydrogen. So if you were to create an electronic excitation in that molecule, it would very quickly relax to a vibration. And so therefore, it has a very short lifetime, no chance to emit. So the other reason why, of course, it's good is a priori, since it's a very high-cost technology, maybe even if we make something that's a little bit not as good. But let's say it's 100 times cheaper, then it has a potential. So this is where the technology chart is for infrared detectors. This is the fundamental limit of detection where the background generates the noise. And the curves you see here are from the traditional mercury cadmium telluride detectors. They are at the background limit. They're as good as they can be. But they all have to be cooled to liquid nitrogen. And the reason is that as you raise the temperature, you create carriers by thermal excitation. And those carriers give you, of course, a lot of current. They also give you a recombination. So when you photoexcite, you create another carrier. It might let's say an electron might recombine with a hole that was thermally generated before. So it goes, the lifetime gets very short. The efficiency becomes very low. But the other problem is Auger recombination, which is where the recombination rate is growing in a nonlinear fashion with the thermal density of carriers. Okay, so these are the best, but as I said, they're very expensive, and this is where we are now with the colloidal quantum dot. So I think we're quite close to reaching we have reached the background limit, and we now have to see whether we can transform that into a technology. So our efforts to move into that direction started actually quite a long time ago, about 15 years ago. And what we did was to take the cadmium selenide, the standard colloidal quantum dot system, and verified that we had indeed strong infrared transition called intraband transition. So to do this, to observe them, we had to somehow put an electron into the state. That was before we had invented the electron transfer method. So we put the electron into the state, and then by infrared, we're able to probe that this electron was here. So there's transient pump probe experiment with lasers. And what we could see indeed is this very strong infrared transition where the sample became effectively totally opaque at some specific infrared band after photoexcitation in the visible. So this is nice. And so you could imagine if somehow you could inject electrons into the system, then you might be able to make an infrared detector out of a material that is otherwise transparent. That would be kind of cool. You could use zinc oxide, totally transparent in the visible, but somehow you could make it an infrared detector. So you could see through your goggles, and at the same time, you could have another image superimposed, which would be a thermal image. That would be interesting. And so I thought this was going to be a very simple project. And the only thing we need to do at the time, 1998, was to develop a method to dope the quantum dots. Didn't think it was going to be that difficult. We also had to figure out how to make transport of electrons through quantum dots. At the time, nobody had achieved conductivity. And there were some other issues, and they're all written here. So this is kind of the picture. We have disorder. There's always disorder in the systems. We never have perfect dots, and they're never in perfect position. And so there's disorder. So we're trying to see a photoconduction response after excitation of this electron here, and hope that this electron somehow is going to transport through that layer of states. But that's not obvious. First, if we don't have an exact doping, what is going to happen? The electron will go here, and then most likely it will come down here, and it's done, over, finished. So somehow we need to have all these states full so that the electron doesn't have a chance to come down unless it meets some thermal excitation. So we need to have exactly 2 electrons per dot, no more, no less. We need to have conductivity, okay. Now we've solved that a few years later. And the other problem we need to know is the electron is excited, but it has a high probability of coming back down as well as hopping over. What is that probability? How fast does the electron come down? And when we started, this was not very promising. The electron was coming down in a picosecond or less. So a picosecond is pretty short time. It would require mobility which are as high as the highest mobility presently achieved to have an electron hop over in also a picosecond. So that was not certainly possible. So we thought about this for several years, 12 years, didn't make any progress. Eventually we gave up, and we moved back to the simpler idea of using quantum dots that would be made of a material that already had a band gap in the infrared, quite far. And so there are several ideas, and all of them a priori are workable. One could look at alloys of lead, tin, selenide and telluride. These alloys have very small band gap. Alloys of mercury cadmium, the ones that are used to make the commercial quantum detectors. Alloys of indium, arsenic, and antimony also. So these are traditional materials that have been looked at before for infrared detectors. The other approach would be to start with semi-metals, that is, materials that have a zero gap, but a very small density of state at the point of where the conduction and valence band meet. So there's a few of those semi-metals. Bismuth, antimony are elemental such semi-metals, but they're not very interesting because they have a fairly narrow range where the confinement can be operating. Graphene is very popular now and is a semi-metal. And so in principle, if you could make quantum dots of graphene or ribbons of graphene, you could open a gap in the infrared, and you could imagine using them for infrared detectors, and some people are doing that. We were more interested into this mercury chalcogenides, mercury sulfide, telluride, selenide, because they're simple. They're just two elements, so there's no issue of matching the composition. They have to be that way. And then they are zero gap semiconductors, and they have also a very nice conduction band. So those materials had been also developed before for the near infrared by many scientists before, so it's not like they were brand new. And there was also some hopes that we could even improve by using this inorganic ligand strategy developed by my colleague Dimitri to make those particles well conductive without absorption from the molecular vibrations. So mercury telluride, very simple band structure, heavy old band, and an electron band here, conduction band. And so you can see that now all you need to do is, in the quantum dots, you control the wavelength. The wavelength is inversely proportional to that wave vector here. And so the wavelength defines, the size of the particle defines the wavelength, which then defines the energy. And so smaller particle would start here, larger particle would start here, et cetera. And you can see that the energy gets smaller and smaller for larger and larger particle. So we set out to make those particles, and the synthesis was not that difficult. This was work done by a PhD student, Sean Killian, who now works in a startup company to try to make these things useful for infrared detection. So he made those particles, and he found that they were not spherical, but they had well-defined crystal lattice. And they were also nicely monodispersed as far as optical properties are concerned. And so this shows here how the absorption tunes with size. These are particle batches of about 3 nanometer in sizes and about 12 nanometer in sizes, smoothly tuning in size as the particle size gets bigger. The energy, this is wave numbers, so the energy gets smaller. And then those particles also fluoresce. And here we show the typical plots where all the fluorescence are normalized to 1 to make a pretty plot. Of course, it's totally deceiving. If we actually look at how the efficiency varies with wavelength, we see this systematic drop by 4 orders of magnitude as we go to longer and longer wavelength. And so this is actually a challenge that we face at the moment. We do not know how to improve this. It's important that we improve it, because if we don't, we will always be limited in terms of the maximum efficiencies of those detectors. We want to have as high a possible quantum yield to have the best possible detectors. So we're down there when we go into the long wave infrared. It seems to saturate afterwards, but it gets pretty low quantum efficiency. Why is there such a low quantum efficiency? A part of it is the molecular ligands. And so this is shown here. This is one sample of mercury telluride quantum dots, and what we do is change the temperature. And as we change the temperature, the wavelength shifts. That's because of the band structure changing a little bit. And so what we see is, going from low temperature to room temperature, the fluorescence decreases initially. So traditionally you'd say, oh, there are traps or something is happening. And then it increases again. Oh, so we say there's traps or something. So we always attribute changes in luminescence to traps. But this case is not. This case, the change of luminescence is due to energy transfer to the vibrations of the ligand on the surface of the particle. And it's happening exactly where those vibrations are, the CH vibration. And so we're facing the same problem that organic molecules have, except not to such a drastic extent, because we still see some luminescence. And so but eventually we'll have to solve that problem. And so then, with such materials, we put them onto a device, which is a set of interdigitated electrodes, very simple, and make a film of it. This is the color of such a film, semi-transparent brown color. And then we just shine light on it and measure the photo response, and they detect infrared light. So this was our first series of spectra where we changed the temperature, and you can see a small tuning with temperature, the same one we saw with the photoluminescence, and they respond. And we've made some progress, and now this is an example of two detectors, if you will, made with different size of particle. This one detects the mid-infrared between 3 and 5 microns quite well, and this one goes all the way to 12 microns, or even further if we extend that log scale. Signal to noise is really good, and you can even see all the absorption from water in the atmosphere, from the CA stretch, from CO2 in the atmosphere, the CA stretch that's remaining from the ligands, and the water in the atmosphere. So all of this you can see coming out. And this is from the silicon dioxide on the substrate. So they work. They're fast. They're just not very sensitive in that particle implementation. So then we thought of exploring other systems. And since we looked at mercury telluride, mercury selenide, mercury sulfide are just the same in principle. So let's just look at them. And what we found to our surprise was mercury sulfide, well, the spectrum is not very pretty. It's kind of a broad spectrum. This is a peak which is due to the ligand in the films. So they're not very, it's just a molecular vibration. But we also saw this band here, which was a puzzle. Where did it come from? And there were a number of possibilities, but eventually we found that this was what we were looking for 10 years earlier, which was this intraband transition of naturally doped nanoparticles. And so it turns out that this mercury sulfide is natively doped, as it is, in air. It has, for the right size, just 2 electrons into that state. Not only that, but we can change the number of electrons by changing the environment. And so that was a surprise, but it shouldn't have been. So if we take the mercury sulfide and take the spectrum of it as it is coming out of the reaction, we have this peak here, which we assign to that intraband transition. And then all we do is add some sulfide to the solution, S2 minus. And this S2 minus is probably going to bind to the surface of the particle, but it makes the spectrum change by creating absorption in this range and removing the absorption that we had from the intraband. So somehow the intraband transition disappears when the sulfide is added to the surface. So, okay, maybe the electron transfer. But then when we put mercury on the surface by adding mercury ion, then that peak reappears, and so on and so forth. And so what those things are doing is really this. Either we're in these situations when we have a surface that's mercury rich, or we are in this situation when we have a surface that's sulfide rich. So we put electrons in or put electron out. Are we actually putting the electrons from the surface? We don't think so. The interpretation we have of this is simply that it's like the work function change when we put something on the surface. All we do is change the electrostatics around the particle. We have, let's say, a dipole layer that's pushing all the levels up or pulling all the levels down, depending on the orientation of that dipole. And so all that the surface does in this case is not transfer electrons by adding sulfide or adding ions of any kind. It's just moving them up and down. And it turns out that the Fermi level of the environment, where the electrons reside in the environment, where they are available, just happens to be at the right position, such that we can move up and down with respect to that Fermi level, and electron transfers from the environment to the particle. So with the right condition, the right size of particle, and the right environment, we can have 2 electrons per dot. We studied also mercury selenide, same thing, better nanoparticle, better spectrum, but exactly the same behavior. And then we studied the conductivity of those things, the same way we did before with the cadmium selenide, and it works even better. So just to give you a little picture of what we do, this is the interdigitated electrode. We're going to put a film of dot on it. We put that inside a cell which contains electrolyte and a counter and reference electrode. And then we apply a bias with respect to the reference electrode, and we measure the current coming out of those two sets of digits. Conduction is the difference. Total electrochemical current, how much charge is injected inside the film, the electrochemical aspect of it, that's the sum of the two currents. So what we see with the mercury selenide is a very beautiful electrochemistry where we have a wave corresponding to electrons going in that first state, and then another wave where electrons go into the next state. And it's reversible. But at the same time, we can look at the conduction, and we have this very nice shell-to-shell conduction with a peak in the 1s state and then a peak in the 1p state. So the same thing that I showed about 30 slides earlier, but now with mercury selenide. And the systems can then be used to detect infrared radiation. So this is a film of those particles, dried now inside a cryostat. We measure the absorption of the film. This is the black line, contains some CH contamination. We measure the photo response of that film. It's not very good, it's noisy, but it's exactly at the same position. And then we cool the system down, and we measure the photo response again, the full current. And now we have this very nice, very low noise response, which is slightly blue shifted. So this was very exciting. It was the first time that we had seen something coming from those intraband transition, which was the kind of dream I had about 15 years ago of hoping to do, but couldn't do it then. This shows the comparison between intraband, the red one, made with mercury selenide detection, and interband, made with mercury telluride. Which one is better? I don't know. They should both have the same fundamental limits, the same fundamental advantage. Narrow is good if you know that that's where you want to detect radiation, because you don't detect the radiation outside, so it's less noise. So there could be applications where this would be better than the intraband one. So I'm close to the end. This has been intraband photodetection was kind of the goal or vision that I had about 15 years ago of wanting to achieve, but it took a lot of time. First, we had to find that there was such a thing as an intraband transition. Then we had to solve the problem of putting charges or doping the system, and we found a partial solution with charge transfer doping. Then we had also to make sure that we could get electrons flowing through a film of dots, and that led us to the ligand exchange, and then the ohmic conductivity. And then we had to understand this very fast electronic relaxation in those excited intraband state. And so we understood to some degree that ligands mattered, that we could have some sort of energy transfer between the electronic transition and the surface ligands. And this work was actually done by Anshu Pandey, who's now at the Indian Institute of Science in Bangalore. And then we had finally the last step, which was really difficult, and we struggled many years trying to think of how we do this. Well, nature gave it to us. We didn't plan on it. Nature just happened to make mercury selenide and mercury sulfide quantum dots naturally, natively n-doped. And so then it worked. Now, if we want to go further with this, we have to go after that figure of merit, which is called the detectivity. And detectivity is a measure of, it's 1 over the minimum detectable signal, which is basically the noise of the system. This is the formula for it. One can relate this to some basic properties of the material, such as the lifetime of the excitation, the absorption, the inverse absorption length of the material, the quantum efficiency of charge separation, the wavelength at which one operates, and the number of thermal excitations. That's one way of calculating this. And we can calculate this for the nanoparticles. And in principle, we should do much better than the bulk as far as tau is concerned. We should do the same for alpha, the same for eta, and the same for n. So in principle, we have a fundamental advantage over the bulk material. Now, where we want to go is when this is limited not by the intrinsic noise of the material, but by the background. So this is some sort of a benchmark, that if the noise, the fluctuation of the number of photons coming onto the detector is the limiting noise, this is the benchmark. And so we just recently got there with the mercury telluride quantum dots. So they were photovoltaic devices. And so what is shown here is a number of features about those materials. When you cool them down, the open circuit voltage increases in some sort of monotonous fashion. The short circuit current increases up to its peak value, but then it decreases again. And the reason for the decrease is that the charge carrier separation gets worse as you go to lower and lower temperature because it takes longer and longer for the electron to hop. It's a thermal activated process. So as you go to lower temperature, the electron is kind of stuck inside the particle. So the efficiency of charge separation drops dramatically. At least that's how we understand this drop. The devices are fast, about microsecond time response, not unexpected given the mobility. They're linear, which is a nice thing about photovoltaic devices. The response is linear with power, and that's important when you do imaging. And they can be tuned by just changing the size of the particle, so that's pretty nice. And this shows the last data slide. This is the IV curve of such a detector. The black line corresponds to the detector cold, so it's inside a cryostat, but the shield inside the cryostat is closed. So it's surrounded by only cold radiation. And so there's very few background photons coming onto the detector. The shield is open, so now 300 Kelvin radiation can just come in and excite the detector. And so that means that this detector sees background radiation. And the noise, in this case, is limited by the shot noise of the current at this level, and that's background limited condition. Now this detector is sensitive enough that if you put your hand in front of the window of the cryostat that houses it, then it can definitely see the increase of current just because the hand is slightly warmer than the background. I'm not sure that would be true if we were to put it outside on the street, because I think the background is hotter than the hand in Delhi right now. But in Chicago, it works really well. So, and then the red line is when we just shine a black body radiation at 600 degrees Celsius. So not hot enough that you can see it glow red, but quite hot and not very far from the sample. So just blast the thing with light. So future improvements in this topic. We need to control the non-radiative relaxation. This is very important. This is this issue of the quantum yield dropping dramatically. We will need to learn better how to use the surface to modulate the Fermi level. We need to improve the device structures. And we need to monitor the Auger relaxation, which is why, a priori, these materials are much better than bulk. And I think we will have a technology for infrared. Now, what next? What next? And that's not only a question for me, that's a question for you, PhD students, scientists. We all ask ourselves the question, what next? When you achieve something, you think, I've been dreaming about this for 15 years, what next? Well, first, I think we need to find something, a goal or a vision of something we want to do. And I think we should not follow the crowd. Now, it's dangerous to not follow the crowd because you might end up having nobody interested in what you do, which is what's happening to me at the moment, but I think it's going to change. Nevertheless, whatever you do, we need to do careful and reproducible work. That's very important because as long as we do this, we contribute to science. Otherwise, we just contribute to noise. And there's way too much noise already in the field of nanomaterial. But if we do careful, reproducible work, then we have a contribution. Maybe very important, maybe not important, but at least it is something on which people will build. Now, in the narrow topic of colloidal nanomaterial, the basic chemistry studies will be of lasting values. I'm not a chemist by training, so I went into this field because it was easy enough for a physicist to dabble into it. Many of you are well-trained chemists, and you can make significant contribution. I think it's more important than just trying to make a device 0.1%, 0.5%, 1% more efficient. I mean, unless you can right away go to the maximum efficiency from ventilation. But small increases in efficiency are maybe not as important as the chemistry you bring to the system. Oh, keep an open mind for serendipitous discovery. There's still a lot to do. And sometimes we get locked into a certain direction and we can't realize that we just observed something interesting. And from a more physical aspect, basic understanding of the physical concept is still really important. And we need to demonstrate that those physical concepts apply in systems that are well controlled. So there's always this joke that chemists do very simple experiments on very complicated systems, and physicists do very complicated experiments on very simple systems. That's a nice way of telling that joke.